here for where you come from. It's great to see some old friends and also some new faces. We're sort of doing a round robin introduction, but that's going to take quite a bit of time to do that. So I'm just going to introduce myself, Tony Cohn, PI of the project to begin with. All the speakers will introduce themselves as they go through. If you have questions to the floor, please introduce yourself and where you come from or your interest. So I'm going to start with just a few bits of introduction to the whole project and the day. Then Ant will take over with a longer overview of what it is we've done, and that will act as an introduction to the student presentations. So, also just point out we have Elaine here who is going to be videoing and transcribing things, so we have a record of all the interesting things that everybody's going to say. Don't let that make you nervous. We've just reported enough events, but we really want to make sure we don't miss anything from benefiting your interactions with us. So the format of the day is that in a few minutes, then we've got 3 presentations from Dan, Birmingham, Rob from Bradford, and David from Leeds. Then Ant's going to a short production that we put together. Going to say something about modeling the data. I'm going to give a few words about what we might do with all this data, and then we're going to open up for a discussion until lunchtime. We're going to try not to take just questions to begin with. We're going to try to reserve all the questions. So I know you'll be itching to ask people. Just make a note and then come back at that point at 12 o'clock, okay? And then we can bring it all together. I believe that Chris is going to be trying to keep us all to time today.
You did agree on that. I do have a whistle for you.
In the afternoon, we then move to the wider scope outside the DART project and how the things interact with the community. And we will have more introduction to that later. So we hope to wrap up by 4:30. So. Why are we doing that? Well, about 4 years ago, we put in this project in response to an AHRC Arts and Humanities Research Council and the EPSRC Engineering and Physical Science Research Council bid for science and cultural heritage. And it was very open. You could do anything. There were people who got funded to build electronic noses, who do visualization of bits of archaeology and old buildings. It's all kinds of different things got funded. This was the only one that was really funded of this kind of archaeological bent in terms of remote sensing. And what we were interested in doing, as we say here, was to really get a better understanding of the formation of stress marks in fields, which are caused by densities. And this was to try to understand the science, but also to try to then influence how the community goes forward and result of that better understanding. And so we've now kind of reached that point where we've got all the data, we're trying to understand it, and we want to think about how we're going to make use of what it is we've learned. So there's the kind of formal side of the presentations that are going to be coming up from the various speakers, but also, I mean, there's going to be coffee breaks, there's going to be lunch. Please interact, please just have full discussions in the discussions. The PhDs are kind of nearly finishing, but they're going to be going out into the community, I hope, and taking their expertise from DART to there. So I think, was this the point you were going to take?
I think this is where it comes over.
Yes. So I'll be talking again later, but I'll let Ant go forward now.
Okay, so I'm going to give you a whistle-stop overview of the project and its inception. We have a large consortium, including academic investigators, consultants who can provide us with a whole range of insights to new advances and new techniques, a number of heritage professionals and industry professionals. Pointed out both Dave Cowley and Roger Palmer, as I did from the first workshop, because without their support, this project wouldn't happen. We have our 4 PhD students, 3 through DART, 1 through Department of Bursary at Birmingham. These are very original projects. These have changed a little bit, but I'll let them tell you exactly how. We have a whole range of different people who make this work. I don't expect you to read these. I'm not going to go through each of these. These slides are online, so you can go back and you can refer to them. but we've had a number of different industry involvements. I do want to bring out Van Volt, Allied Associates, Leica Geophysics, and Luxi, have all supplied equipment and support, and so I do want to say thank you to all of them. And we've had a number of other academic collaborations, and I have updated Jordan in his, sorry David. There you are. So, you know, from the outset, we've been a project that's trying to be inclusive, not just within the academic arena, but throughout the whole stakeholder community. So, a quick project overview. We've been focusing on contrast identification, the physical, chemical, and biological variations that lead to the formation of features that we want to detect with our equipment, which we can do directly or by proxy. It's not well understood. Data's been focused on trying to understand those a little bit better and to put them within their environmental context. To quickly go through to this slide, this is looking at aerial prospection, so you can look at variations in crop canopy height. You can look at differences in crop colour. You can look at variations or micro variations in the topography, and you can look at variations in soil colour. Equally, you can look at variations in thermal effect, and you have these lag effects over time. So the way that we can detect these contrasts varies depending if we're doing directly or by proxy, and the kind of sensors that we're using to detect those elements. We have a number of different work packages. Again, you can go back and look at this in detail. We've achieved most of them. We have some question marks against others. Again, this workshop is an opportunity to look at some of those question marks in a little bit more detail. We have a number of milestones. Similar thing. We've achieved most of them. We have question marks against some. And again, this workshop will help move that forward. Communication infrastructure. We have a website. Amazing project with a website. But we try to do this in a way which aggregated our information. We share stuff internally. We have an internal Dropbox-esque component. We have a whole heap of structured email lists. We'll talk about the open science bits later on. But we also deposited all of our data into public environments. So videos on YouTube, documents on Script, bibliography elements on Mendeley, presentations on SlideShare, photographs on Flickr, general conversations on Twitter. Because these are open with open APIs, we can actually access them and aggregate them through our website. So our website became media rich because we were linking it directly through to the media, which we were putting up as part and parcel of the project. It's nice. This is where I'm going to spend most of my time. This goes into the science and broadly about what it was we were doing. We had two sites, one in Diddington in Cambridgeshire and one at Farm Hill in Cirencester. Diddington site, there's Diddington itself, you've got the A1 here, you've got a loam area to the east of the A1, you've got a clay area to the west of the A1. We did some preliminary geophysics, but essentially what we wanted to do at these sites was find locations where we had both heavy soils and free draining soils, so that logistically we could visit multiple sites in one day and look at those major differences between the heavy clays, which are difficult to detect things on, and the loamy free draining soils, which are easier to find at least crop marks and other anomalies. We did initial magnetometry surveys, identified areas which we'd like to go in, did initial coring so we could find out, at least begin to characterise the features that were there. Similarly, over in the clay area, sorry Rob, this is probably not stretching the way that you'd like it to do. That's what you do when you get cross-disciplinary work. This is the area of Palm Hill, and again you've got your clay area over here, and your loam area down here. This is a field called Cherry Pops. Lovely, lovely Roman villa. It's right down here, and lots of very, very nice field systems. So that's where we did our coring, and that was where we wanted to our trench. More about that later. And this is quarry field. Not very exciting field boundary, but it's essentially going to show the processes. So, of wriggle furrow field running across there. The general framework was to dig a hole, insert temperature soil moisture sensors, both in the archaeological feature and outside of the archaeological feature. Oh, this is the ditch. Close to that, because we've got some Inco TDR probes that have been invented by Van Volt, and we also bought a companion set. We could do a comparison between those probes and the information from Birmingham's TDR. Sorry, the jargon will be explained in a bit more detail. We had a geophysics survey area, so on a monthly basis we're going to stick geophysics close to the areas where we're doing our monitoring. And then we have a spectroradiometry area where we essentially measure electromagnetic variations across the spectrum on translates across the area. On top of that, we'll be collecting both vertical aerial photographs, hyperspectral imaging, and full waveform and discrete return LiDAR. So we're getting multi-temporal collection of both in situ data about what's going on at the feature level, all the way to what's going, how that's been impacting our overall crop growth and changes in the market. Okay, so top we have our as design for the probe installation. So we're looking at getting both TDR, time domain reflectometry, from which we proxy our soil moisture, and temperature probes going down the archaeological feature, and then further probes outside the archaeology with a lateral offset as well, so we can look to see if there's any variation, if the archaeology itself acts as a sponge effect, changing the localized soil moisture or temperature characteristics. The INCO probe, because it's a core-based, core-driven probe, you just put your core in, put your probe in, and then log it, and it runs it down there. So that's the as design, and this is an example of the as build. See again a bit more about later on. For the well-drained soils, we had 8 and 8. For the clay soils, we had 16 and 16. So we could characterize the clay in a little bit more detail. And so we resulted in something like this. Again, you've got your ditch feature running through, your excavation area, your TDR and temperature probes, your geophysics area, and we end up collecting a whole heap of different data at different temporal intervals. Okay, so here's the general picture of the UK. There's Cambridge, there's Harm Hill, there's Diddington, there's Harm Hill. We've got a split between the drier area in Cambridgeshire and the wetter area in Cirencester. And if we go down into each one, okay, go back into Diddington, again here, so you can see it's an arable environment. And this is our clay field. So we have our geophysics area. This is the place where we had our INCO probes. This is where the excavation was. These are where the boxes are for TDR. This is where David did his spectroradiometry. Move in. And this is our section profile. So you can see the areas where we took out the samples. One thing I didn't say, actually, in the previous slide, which I should have done, samples are taken away for laboratory analysis, where we did particle size, we did loss of emission, and we did basically synthesizing the whole raft of laboratory measurements. Okay, down at the pasture field, this is on the free draining area in Diddington. We had our initial area of excavation and installation, similar setup here in 2013. This is the geophysics area in 2013. We did a characterization trench in here and took more samples out. So we could actually take samples directly over the area where Rob had been taking his geophysical measurements. Interestingly enough, our section profiles, which are very clear here, are somewhat different. Even though it's about 10 meters away from the original trench. And so one of our assumptions was that everything would be similar, quite close by, slightly blown out of water. This is Harm Hill. This is quarry field here. Again, similar setup, geophysics area, spectroradiometry, trench. We also have, we undertook a thermal experiment in this area, so we did dynamic measurements over a 4-day period. Here's our scaffolding, and here are the areas where we took those thermal experimentation, and that was with John. That's on that section. And finally, this is cherry tops. Now you'll notice, if I look out, that we were going to be going in down here. The villa area was scheduled a week before we went into excavation. Lots of telephone calls were held, and we decided that unless we wanted to basically write lots of paperwork going on a monthly basis, we wanted to take geophysics, it was just. But we shifted over to an old field boundary here. So, same as we've got the excavation area, geophysics area, and we also did our on the spectrum agriculture. And quickly into the achievements. We've achieved a lot, so much you can't see. We can zoom in, but again, these are all online, so if you want to go into a little bit more detail, we have lots of data. Most of it is available online in a repository. I will be showing this later on. We've attended lots of conferences and gone to workshops and such things. We have publications and presentations, there will be more. And we've done other stuff too, people trying to improve impact in the media and in public. Okay, that's us. My whistle stop tour done. This will all be available as a mind map. I will send links through to everybody at the end of this event. If you're happy, I will send delegate details around to everybody. If you are not happy with doing that, find me and I will do it. Well on time as well.
I don't have to tap dance for 10 minutes or something. I've actually just gone and Googled DART meeting 2013 and just to try and find out what the programme was, because I didn't catch it on the first slide. And actually it came back, one of the first things was DART's World Supremacy 2013. Am I at the right meeting? We obviously do have a few minutes to perhaps quiz Anton on some of those issues that he just raised. And don't know, perhaps it seems that we perhaps should move on a little bit and hear from the PhD students, because actually they will flesh out a lot of the issues that Ant's already shown. Is that okay?
That's fine, I mean.
In that case, let's just pass straight on. Dan, are you up next?
Oh,
excellent. We've got three students who will be talking today. Obviously, they're being linked via this particular project, although there are three different institutions now as in civil engineering in Birmingham.
Hi, just to introduce myself, I'm Dan. I'm looking at the soil, electromagnetic radiation response. Just as a bit of a sort of thing to limit expectations, if you like, this is very much kind of work in progress at the moment. So by all means, I don't have all the answers at the moment. But I'll just show you some of the, so I'll talk about what I've been doing, how the research is developing, and hopefully we'll get some answers one day, a final definite. So why electromagnetic radiation? Well, DART is essentially focused on improving the detection of archaeological sites, both using remote sensing techniques and geophysical techniques, all of which really rely, or certainly a lot of these rely to a greater or lesser extent on the reflection of electromagnetic radiation. Now, whether that be ground penetrating radar, or your visible spectrum, or your low frequency electromagnetic scintigraph systems, EM38, mini explorer and things. But the thing is, they've all got different operating frequencies, which is a bit of a pain. So just a bit of physics, which any implied signal proportional to the incident signal, a reflection coefficient, which is defined from the impedance, which you can calculate from these things here. Essentially, your impedance relies on three main things. You've got your magnetic permeability, got your bulk electrical conductivity, well, your electrical conductivity, and your dielectric permittivity. Generally speaking, we tend to consider the magnetic response not to change too much on a seasonal basis. I don't think anyone's properly proved it, but I think we have an inkling it doesn't change too much. So, but the other two do change. Therefore, recording them is obviously important. The other thing they do is they affect speed and the attenuation of electromagnetic radiation. Now, the thing is, these are dependent on the soil conditions, which change throughout the year, obviously, seasonally, and following things. So what I basically had to do is come up with a way of instrumenting the sites to monitor this on a sort of a regular basis, sort of like over the whole year. And what we decided to do is we decided to put in time domain reflectometry curves, the legendary TDR curves that I'm just talking about. I'll just give you a quick rundown of how they actually work. Essentially, what they consist of is they consist of a pulse generator, a timing circuit, and an oscilloscope, and a coaxial transmission line. And what we do is we send that EM pulse down the coaxial thing to the probe. See here, here. At this point, because you've got the impedance change at the start of the probe, and the impedance change at the end, you can identify these points. So you start here and you end here, and the time between those gives you a travel time, which you can use to determine the electric permittivity. The other thing we can do is do an analysis of how much of the energy is lost. And if we leave that for a long enough time, it should roughly approximate DC conductivity, so we can measure that as well, which is an opportunity. So we instrumented the ground with these, and what they do is they measure from each of those probes every hour, and they take one for relative dielectric permittivity and one for bulk electrical conductivity. The dielectric permittivity can then be used theoretically to calculate moisture content, because to use a mixing model or an empirical model, because water is by far got the highest permittivity of things in the soil. You've got air, you've got solid particles, you've got organic matter. Air is roughly 1, solid particles are roughly 3 to 5, and organic matter also about 3 to 5. But water's 80, so it responds strongest to changes in water content, which brings us on to what affects permittivity and conductivity. So you've got water content, which variations obviously based on rainfall and climatic conditions. But as well as just having differences in water content, there's also a difference in how water behaves when it's in the soil, because it has interactions with solid particles. So it binds itself to the surface of them, which adds an additional complication. What we're doing with our models and things like that. Basically, contrast and soil water content tend to be affected by differences in either the maximum storage capacity of the soil, how much water can it hold when it's saturated, which is based on its particle size and things like that. And also differences in infiltration. You know, does it infiltrate faster through the ditch? Can it not infiltrate the natural whatever? So it's worth looking at both of those things. So you've got storage which shows a higher reading for a long period of time, sort of thing. It's storing more water at that point, and you've got infiltration which will show us a faster rise after a rainfall event. We can look at both of those. The other things that affect our response, the frequency of the signal, which depends on the instrument we're using. Now with TDR, we're firing a broadband pulse, so it's got kind of like a range of frequencies carried within that pulse. So we can only ever approximate it with whatever the effective frequency is, which is quite difficult to define, which is a bit of a weakness of the TDR method. As you can see here, at different frequency ranges, different types of polarization mechanism are taking place, and different loss mechanisms are taking place. So we've got a real part here and an imaginary part here. So these are essentially losses, and these are essentially storage of energy. But you can see even within the TDR range, there's a big variation. And what that effective frequency is actually sometimes very difficult to define, so it's worth knowing about. The other thing that affects our permittivity and conductivity is soil temperature, which obviously varies on both the seasonal and the diurnal pattern. Temperature tends to affect the behaviour of the water, because you've got higher ion mobility, which increases the conductivity. It also affects the type of soil you've got, how big its surface area is, things like that. And to a greater or lesser extent, if you go to the literature and read what effect temperature has on conductivity and permittivity, the extent of its importance is very much debatable. Everyone agrees it has an influence, but whether it's a strong influence or not so strong influence, you know, worth checking out. So I'm going to show you some data. So I've already shown you this. This is Diddington Clayfield, which is one of our sites there. As the name suggests, this is one of our heavy soils, our ones that don't drain well, theoretically don't drain well. So you can see where we've got the probes. So we've got essentially 16 in the ditch here. And what we do is I take that by depth at the moment. One of the things I've done is I've taken the potential of evapotranspiration away from the rainfall. So you can see here it's drying. It didn't make much sense when I put just against rainfall. So I basically took it away because it's useful to be able to see the bits where it's almost not raining. So you can see here there's a big drop. Basically, the first thing to say about this is actually we didn't realise it at the time, but actually this took a long time to settle down. So you can see this bit here is all flat, except on the very top. If we go down, it's flat for even longer. And essentially, it's not until you get this first wetting from that you really start to respond to anything. I think a lot of that is the installation of the probes in the middle of the ditch, and we left the ditch open. We put the probes in the side of the space, and we dried it out. And so we took a lot of the residual moisture content out. So the hydraulic conductivity was like really low at that point. It really struggled to transmit water until that actually happened. And once that happened, it seems to settle down a bit, and we actually start seeing some kind of response. But if we go back to you see that most of the response is near the surface, obviously. And lower down, it doesn't respond except sort of after a period of quite extreme drying. So if there's a lot of drying, sometimes it responds lower down. But I think the main thing to take away from this is it seems to be holding the water mainly towards the bottom of the ditch here, but there isn't a huge difference at many points after everything's settled down. The other things to say, the archaeology seems to settle down a little bit faster. So you can see this doesn't have that big initial weather until much later. So it seems at least in the first instance it was not settled through that. To look at the conductivity, you see actually fairly similar trends on the whole. That it seems to be mainly affecting the near surface. But again, we've got that problem of settling. The only thing I can really say is essentially the differences again at the bottom where the moisture seems to be being held to a greater or less extent. And these are sort of like almost, I think these are slightly at the bottom of the ditch, sort of the natural below. So natural is not a word. We've got kind of an archaeology surrounding soil matrix, I think I'm calling it for the time being over in the side. And you can see even when this bit's flat on permittivity. So this is fairly flat, but on this one, even down the bottom, there's a slight curve here which suggests there's a slight temperature response there as well. So I plotted everything, electrical conductivity, apparent permittivity, and then the colour according to temperature. And you can see there's almost no relationship. The relationship between temperature and permittivity seems pretty small, but the relationship between temperature and conductivity is much higher, particularly when the soil's wet. See that that's the archaeological terms. So yeah, the other thing we can do is temperature probes, which we measure every half hour. And you can see nothing you really wouldn't expect here. And the fact that we're missing some data here from where I can get a lot of working version. But essentially it tracks the air temperature, and there's definite heat working down to the only other thing to say is the archaeology responds to a slightly greater extent here and here. It tends to be slightly lower here, and slightly higher here, which I wouldn't expect. It drops off the depth. One of those sites. This is the other site that we did into pasture field. This is the well draining site over at Fleet. So you can see this was mainly sort of sands and gravels, again, you've got a similar pattern. The only thing I can really say about this is there's a rather interesting thing going on here, which I don't fully understand, but I actually think there's a point where the water table comes up. That'll be the one. I don't quite know what's going on with this. I'm still investigating that. What's going on. But again, it takes a surprisingly long time to settle. And start responding normally. Same with the conductivity, really. But again, the main difference is sort of like 0.8 meters. They're down the bottom of the ditch. It seems to be where it holds the great difference, which we kind of expect because topsoil is kind of fairly. I mean, this site wasn't plowed, but topsoil. And there was this sort of capping layer here. Go right the way across the side, and I'm not sure. I don't know whether we ever decided quite what it was, but it's quite fun. Again, I've done this again. See, this never gets as high percentage because it's not as much moisture, but the patterns are pretty similar. Same with the temperature, except there seems to be very, very little difference between your archaeology and your surrounding soil. Here, there seems to be very little difference. So the other thing we can do is obviously look at infiltration, which we've been doing. So one of the things I've noticed is that there's different types of infiltration. So you'd expect our coarse grain soils to redistribute this manner. So if you take that as time 0 after the rains, time 1 and time 2, afterwards, you tend to find it goes down as a sort of like continental, whereas on a fine grained soil or quite shallow depths, you tend to find it desaturates the surface as it goes down. Now if we go back to those other slides, you'll see that both of them seem to be responding more like fine grained soil, which is a bit odd. So one of the things I've been playing with at the moment is trying to work out what the lag is between raining. So I've done some loads of events, but this is something called autocorrelation, which essentially correlates things with the time lag. So you can see at what point it responds. You can see here, obviously, this is an hours. It's quite a thing. As you go down, it takes less time, but you can see there's slightly faster in the archaeology. It's less, but by the time we get down there, there's no real pattern at all. Same. The other thing we've had the opportunity to do, because Bob generously lent us one of the implement programs, is compare our TDRs, which are measuring permittivity and conductivity, with their info probes, which measure moisture content from the travel time, and conductivity, or some kind of measure of conductivity anyway. So what we did, we required a polynomial from them which turns their moisture content back into permittivity, because everything's done in build. And it gives us the opportunity to plot them against each other. So you can see this is a small period, but it's not atypical. You can see that basically their probes tend to respond to it, our probes tend also respond to it there. But there's a difference in absolute values, which is interesting. But essentially the trends are similar. And we did the same thing with conductivity. Now, conductivity is an interesting one because mine are all down here, and theirs are all up here. So they're measuring in millisiemens apparently, and there's vastly higher. So if you plot it on a logarithmic scale, you can see it's still following the same trends. But there's a difference in the absolute value, and it's probably something to do with the way they calculate conductivity. But we're not really sure how they're doing it. But I think it's indicative of trends, but I'm not sure about the absolute values. So the main advantages of the INCO probes are obviously they're much faster and easier to install because they go in as a core rather than having to dig a trench and stick probes in. They don't create any soil disturbance. They include identifying trends and both volumetric moisture content and bulk electrical conductivity. And they come ready with a telemetry system. There's a much simpler interface to get the processing of data. But the disadvantage of them, I would say, is that they have a pretty undefined measurement volume, being that plastic tube. And that plastic tube and electrode coating makes the conductivity determination a little bit problematic in terms of absolute values. And the other thing is the model was built into them doesn't necessarily fit all soils, and you might have to empirically calibrate them in order to overcome any problems in that. I think what you've got to ask yourself when you're installing anything is what's the overall aim? Tracking the relative changes is what you want. They're a good solution, I think. So what have I learned? The greatest difference seems to be water held at the bottom of the ditch, I've shown you. The magnitude of the difference is greater than coarse grain soil, which won't surprise anyone. Infiltration tends not to affect below the top 30 to 40 centimetres on either side, that's looked at so far, except in cases of extreme drying before hand. Temperature has a minor role in relativity, but the larger one would be particularly in saturation. I think a lot of what I've learned is actually how to monitor soil properties long term, because ultimately I lost a lot of these sensors. Flooding, animal damage, and obviously that settling issue I showed you that maybe you need to install them either a long time before or when it grows in. And my work's still ongoing, so I've got the two sites of the REC and Siren system to look at, and I need to start linking this behaviour to some of the soil lab work, which Laura's doing at the moment, and make some conclusions based on that and better understand what's going on. But I'm still looking at things. So just to say thank you to a few people, I've got to say thank you to Landau, obviously, for lending us the info codes. I'd also like to thank AC Electronics for lending us a radar. We could do a couple of radar surveys which I haven't looked at or anything. But it's kind of good to learn some equipment. And also just to thanks to some of the other people that helped.
We'll keep on moving through and we'll take the discussions at the end of this. So next on we have WorkshopAM, who's getting refreshing. Rob's from University of Frankfurt and will tell us about some of the cheapest formations.
Yes, I'm Brian from St Bradford. I'm basically looking at the sort of more geophysical above ground measurements that we've taken throughout the project. Specifically on the issue of resistivity and electrical imaging, and centred around the idea of a seasonality problem investigating different soils. The seasonality problem with resistances is well known within the community. We know that at certain points of the year we can see a ditch feature with our resistance measurements, and at certain points of the year we can't. There has been a few studies taken which have mainly looked at big ditches on easy draining soils, and they tended to come to a conclusion. To me, it seemed like an extremely simplified overview of a problem that's much more complicated than that. And with DART, we have the opportunity to look at multiple ditches and much more communal gardens, small ditches on both our free draining and our very difficult places. An example of the difficulty with the problem is the current English heritage guidelines, which helpfully suggests that the West Coast survey was where moisture contrasts are at the most accentuated, which is very true, but not very helpful in practical terms. So hopefully in this presentation I will introduce to you some of the data we've collected, introduce a new methodology I've come up with quantifying how we can look at the actual response we're getting from our teachers. I'll then look briefly at some weather estimates to see how the contrast factors with our resistance measurements correlate with the weather. And then I'll try and investigate whether we can specifically look at different soils within our ditches to see if we can fully understand why we're getting the response we want. So we did a resistance survey over our sites. So we're using this sort of Zimmer frame device. We actually took a multiplex survey, which means we increased the spacing of our electrical probes, which essentially gives us slightly increased volumes of soil to look at each time. And this is basically a page of all the data we've collected, simplified into box and whisker graphs. It's maybe not the most useful slide to have obviously a lot of information there, but the biggest thing to take away is the idea of seasonality. This is just our data, this isn't digital, this is just the whole data set. We can see that we're getting a very non-seasonal relationship. If we zoom in to, say, this section here, that's our entire fieldwork season. This is the resistivity of the data from June 2011, and that's the resistivity of the data in June 2012. We have complete different contrasts in the same month, and different apparent resistivity measurements as well. So we're not seeing the seasonal data set. In fact, it's basically peaked in July 2011, and the resistivity basically just dropped across the site throughout the whole survey season. Granted, it wasn't a very seasonal building season. So this is some grayscales of that data. Each square is a monthly survey. We've got our high hill sites up here, Eddington sites down here, free draining and clay. What's hopefully quite obvious straight away is that our free draining soils produce a nice ditch anomaly, this negative white anomaly going down through the data set every single month, nice and clearly. At pasture field we have this sort of more triangular feature, because this is actually two ditches coming together, and this is the junction of those ditches. Again, we can see that essentially every month. At quarry field, our clay site, we're seeing a ditch every now and then, and some months we're not really identifying it that well. Interesting as well is that it's a positive feature. It's actually coming up as a black feature, so a positive, a high resistance anomaly. Tiverton clay field, I thought we'd never see the ditch, but in our last month, we saw a nice negative anomaly coming through to the average feature, which gave me lots of joy. Seems like a bit of an issue there. So basically, I looked at the data as if I was doing a commercial geophysics survey, looking at high or low anomalies or looking for archaeological features. And I've actually highlighted the ditch in purple on these ones. So it's quite graphically shows the ditch coming through in all months in our free draining soil. In quarry field, it came through about 60% of the time, and if this wasn't corrupted, you'd see a nice ditch there as well. So only 1 month at Tiverton clay field do we really see it in that data set anyway. So going back to when we see the ditch every month, that's very useful, but what's also very useful is what's the magnitude of that anomaly? How can we quantify how that anomaly might change month on month? And also, in our hard-to-find regions, again, is there some sort of way of quantifying how we can see that anomaly compared to the other months? One way I came up with calculating a new contrast factor was to use a tube method sort of algorithm, I guess you call it. First is a detection test, which takes a sample of the ditch measurements and all the background measurements. And this essentially just looks to see if the two data sets are different, are significantly different. If they are significantly different, then obviously we can detect the ditch in our data set. So basically we can cut off, essentially this all goes down to an R factor, which is basically the same as a correlation coefficient. So a rating of 0 means there's absolutely no ditch there. A rating of 1 means we're seeing the ditch, well, 100%. So I had a threshold of 0.4, and I said if the data shows a mark of less than 0.4, we can't see the ditch in the data, it's just in this. If it's above 0.4, we can detect a ditch. Once we've gone through that stage, we then can see how big the magnitude of that ditch is. And this is essentially taking the line of data from within the ditch and line of data next to the ditch and working out the percentage difference between the two. Once we have that, we can calculate the contrast factor by times in the detection by the magnitude. Well, this produces some quite interesting results. If we can see a bar in the bar chart, we can detect the ditch, and the length of the bar tells us the magnitude of the anomaly. So again, on our free draining soils, we can see the ditch all the way through the year. We are seeing very different magnitudes of the anomaly though, especially over this very dry period we had between September and November 2011. If you can remember, that was actually a drought in the winter. Interestingly, sites on the clay part of the fields, we're getting our best responses from our ditch during that dry time in 2011, but we're only seeing our ditch in some of the wettest months, 2012, in Diddington. So I wondered about looking at the weather data and how to sort of most accurately quantify how these responses are changing to weather. And as we know that, as Dad mentioned before, temperature also affects the conductivity as well as the rainfall. So I actually put together a transpiration calculation that takes a whole lot of the measurements we take from the field sites, the humidity, the wind speed, the temperatures. And I basically take that away from the rainfall, which gives us an estimated cumulative moisture balance from the start of our survey. And as you can see, both sites show similar trends, but are actually quite different. So our site in Cirencester gets very dry, that's our drought period here. But then once we get to about December 2012, it just keeps getting wetter and wetter and wetter and wetter. And actually our last month of survey will be our wettest month. At Diddington, we see a much more increased drop-off. It's a much drier area of the country, as we suspected. And when we start getting the rainfall back again after December, it never actually goes above where we started. So we see a much drier situation than we are at Cirencester. So how do the contrast factors of our resistance data relate to those cumulative moisture balances? Well, I first put the Cirencester data, the Cherry Cox data against the cumulative moisture balance, and got a very disappointing 0.1 negative correlation, which basically means it doesn't correlate whatsoever. However, when graphed, it was noted that these 3 driest months we had might be the thing throwing off the correlation. So excluding those 3 months, we suddenly have a 0.82 very significant correlation to data, which basically I think suggests we're seeing as the soils are getting drier and drier and drier, anomaly is increasing and increasing. But once we get to a certain point, cut-off point, the ditch also starts to lose its moisture, and that's why we then see a drop-off in the anomaly. At Quarryfield, again, we're seeing a negative correlation, so we're actually seeing a better response as the fields get drier. There is no drop-off in the really driest months. In fact, we're seeing our biggest contrasts right at our driest times. And this is especially true for our smallest probe separations, so our shallowest soils, we're seeing the best response. Frustratingly, at Diddington, we're getting an opposite trend. We're seeing a positive correlation to our data sets. So at Diddington, as it gets wetter, our contrasts are getting bigger. I haven't quite worked out why this is happening convincingly yet. I'll have to keep on thinking about that. So that's a brief summary of what I just said. Again, I'm sure these slides will be available. So what have we learned just from our resistance data? Well, there's some common misconceptions. In our data set, there's no seasonality whatsoever. I'm not saying there isn't seasonality in data, as this was a very unusual year, but we're not seeing it here. There's no sort of suggestion that wet or damp conditions might give you the better response. As we saw before, different ditches seem to give you different responses over different weather conditions. And therefore, pursuing some sort of overall best survey time is a bit of a fallacy. It's definitely not. It definitely is very ditch specific, which might make modelling a wider model quite difficult. So where are moisture contrasts mostly situated? Well, I tried to look at what might cause the contrasts. And for this, I incorporated my electrical imaging data sets. For those who are new to geophysics, basically, this works on essentially the same principle as our twin probe mechanism, apart from we have lots of probes that go in a long line so we can get a nice section through the soil at various depths. Now, I went away from the traditional sort of environmental time-lapse methodologies used in geophysics and thought of actually incorporating excavation data. By scaling our excavation plans and putting that onto our data sets, we can start to extract actual data from our contexts. So this is basically 5 of our contexts from Cherry Cop. So I've omitted the topsoil and the natural underneath the ditch. So we're trying to look at what causes our ditch anomaly. Straight on what you can see, these blue and red lines at the bottom follow extremely the same pattern. These are our subsoil and top of our ditch fill contexts, which are silty clay and sandy clay. Now I half wonder if these are actually the same context and actually we're seeing a difference in excavation because of maybe bioturbation or ploughing trends, making that a slightly different colour. I'm actually seeing the best contrast for that ditch in context 9, which is the bottom of the ditch fill, this sort of pink colour. And you'd expect the best contrast there because the contexts 4 and 5 are basically free draining limestone weather geologies. So I thought I'd look closer into this relationship. And by looking at the difference between context 4 and 5 and context 9, with this sort of pattern. This sort of pattern correlates quite well with our contrast factor data sets at Cherry Cops, especially at our 0.75 probe spacing, which correlates 0.7 significant to 0.01 mark, which is quite nice because our context 9 is between 0.68 and 0.92 metres, so it's bang on that 0.75 mark that we want it to be. We can also then cross-correlate this with weather measurements, which found to be the best sort of cause and effect to be after about a 4-week time lag, so moisture conditions at the surface. So our ditch at Cherry Copse is what I would call our textbook ditch. It very much follows the same sort of model that Armin's got in his books about increasing magnitude over dry months, but saturation gives you a smaller anomaly, and if it dries out too much over a smaller anomaly. It's a really nice textbook example of what a ditch should be doing. At Quarryfield, we have a different situation altogether. If you remember a few slides back, you might remember that our smallest probe separation at Quarryfield, shallowest resistance measurements showed the greatest contrast results. And if you also remember, the ditch feature was a positive anomaly, so it's a high resistance anomaly. When I extracted the ERI data sets, all contexts show extremely similar histograms, which we might expect because it's all clays. Even the ditch fills are essentially the same sort of clays as surrounding it. That's why it's such a hard anomaly to find. However, I did notice that context 1 did have significantly higher reading is with it. And when I actually looked at the data, it was actually the data in topsoil above the ditch that was producing these consistently higher readings. So here's the box and whiskers of context 1 around the ditch compared to context 1 just above the ditch. So what we're seeing, I think, here is an impact from what we know, and we haven't spoken about yet, is in the ditch, which is an old drainage ditch, and it's still got the ceramic pipe in it. So I think what's happening is, as we're getting drier and drier soils, drainage ditch is almost acting like a sump and essentially pulling moisture down from the topsoils, which is creating a high resistive top layer of soil, which is why we're getting anomalies, and especially why we're getting anomalies over the driest periods of our survey season. So what can we take away from all this? Well, I think the main thing to take away is each survey area is extremely different. The analysis of details I haven't got into yet here, because I'll run out of time. It's different again, each field reacts differently to the weather, and there seems to be different reasons each time. Cherry Cops is our own textbook model. So I think I may be bringing up more questions than answers with my research. And I'm struggling to work out how we can even make a wider model if we wanted to. Yeah, so future work for me is finish my PhD essentially, and potentially try and look into modelling afterwards. I know Dave Jordan's probably going to do something on this later on, because we start looking into the possibilities. But I imagine there's tons of scope for future research on various soils, various ditches, various features to try and understand this problem a little bit. Thank you very much.
That seems to illustrate the local nature of variation, and probably has a lot for the community actually within the data set. Dave, where's Dave? Dave's going to give us the final speech presentation. What past yesterday, they've taken up all the slack.
Okay, so I'm David Stott, I'm a PhD student here at Leeds. Can everyone hear me okay? Okay, and basically my PhD is on the sort of airborne part of the DART project. And I'm basically looking at the formation of vegetation marks on arable land. And we're doing this using LiDAR data, spectroscopy, both imaging, airborne spectroscopy and ground-based spectroscopy, and aerial photography. So the aims and objectives of this work are to kind of look at contrasts and how they change over time with weather and particularly land use. There's been a slight shift in my work because really we don't have close enough observations to look at the state of the crop as it changes over time. So I've been much more concentrating on how to actually detect subtle contrasts in the different sensors that we're using. Namely what we can detect with sensors and how we deploy them optimally in different contexts. And to kind of cover this, because I'm conscious I'm running out of time. And there are some challenges with the data specifically. There's a very high dimensionality, so the hyperspectral in hundreds of different bands. There's full waveform LiDAR, which is a kind of, again, a hugely kind of rich data set that we can look at. It means there's lots of redundancy and lots of, sort of repetition of where we find things. One of the issues is there's no unique spectral signature for archaeological features. This is a quick example of some of the you've seen before. You see these beautiful sort of green, but actually it's lynchets caused by the pigs walking up and down the electric fences. So if you apply sort of standard remote sensing, brute force computation, classification techniques. You're going to pick up a lot of this stuff, not so much of the archaeology, but that's just something to bear in mind. So the ground-based methodology, basically we're doing spectroradiometry with an ASD field spectrum probe, which gives a spectral profile over the 350 to 2,500 nanometer range, so just the other side of the visible to shortwave infrared, and it's a 3 nanometer-ish sample range, because they're not necessarily truthful in terms of manufacturer specifications. This is the instrument, big heavy thing, all black top. And in conjunction with that, we'll be taking septometer readings, which can quantify the leaf area index of the crop, surface coverage using near vertical photographs, and looking at tillering in the early growth stage of the crop development. So how many little shoots it throws out in terms of blights and and this is a typical field survey, and this is from April last year. We're in Quarry Field in Hart Hill. Everything's covered in mud. We've also got airborne data, so we've got Eagle and Hawk from NOPRSF, we have full waveform LiDAR, auto photography from the survey camera, and we've got similar data sets from the geomatics group as well. We have Casimo spectral, discrete LiDAR, and auto photography from them. And I'm analysing all this using Python software that I'm writing myself, and basically that's to do spectral analysis, namely continuum removal, vegetation indices, and red edge position, and it also sort of looks at the LiDAR data. So I'm just going to give you a quick example. This is a bit I was hurrying on to get onto. More fun. Basically, a quick example from Dinnington in 2011, over the course of 3 weeks. So basically from the 14th of June until 15th of July. And basically you can see these beautiful crop marks here on the ground. These lovely features. You're seeing a kind of variation in greenness. You can see an obvious increase in biomass and the overall height and health of the crop. 2 weeks later, June the 29th, you can see you still have this height variation and the kind of increased development in terms of ripening of the crop over the ditches compared to the areas outside the ditches. And basically this is after the crop is senesced and ripened, just before harvest, and you can see the biomass variation, but there's very little variation in terms of colour. So bearing that in mind and looking at that, I've been looking at spectral differences from spectroradiometry using continuum removal from different absorption features. So basically, considering the 670 nanometer absorption feature here, which is the absorption for chlorophyll, which is where your classic kind of multispectral NDVI is based, where you look at the minima and maxima absorption and reflectance, respectively. And what we're trying to do is normalize out the effects of the biomass and illumination geometry from that, so we can see what affects what. This is half a t-test. So basically the black areas here are, I've got the dates wrong in the graph, never mind, are the 14th of June. So the absorption index is just a ratio between the absorption minima and maxima. And you can see that showing the strongest contrast. The band normalized is essentially using continuum removal to look at the variations in pigmentation, accounting for the variations in biomass. You can see there's very little variation there, and the absorption maxima is just the depth of the absorption feature from the continuum line. So you can see that basically we have change over time, but the biomass sort of remains constant. So essentially, looking at that, I then wondered if we could use a LiDAR to detect biomass variations. Conscious of running out of time, we looked at the full waveform. This is an example waveform from one of our sites. Quite often when you're looking at sort of full waveform LiDAR from forestry or taller crops, you'll actually see a double peak and a lot of variation in the width of this peak. But given we're dealing with a very low and sort of scrappy agricultural crop, we don't really see that much variation in terms of the width of the feature. We see variation in terms of the overall sun intensity, which is essentially what this is doing, but I'm just essentially going to gloss over this. We see a good correlation between sun intensity and the archaeological features, but the best we get is from the vegetation height. And essentially we're deriving this by looking at the discrete return LiDAR data. So this is a quarry field at Hart Hill on 23rd of March, where there's bare soil. We have one LiDAR survey there, and what we do is we subtract that from the survey on the 20th of June, where we have a mature wheat crop. And there again, it's a survey, and you can see some little bits of variation in the crop canopy. That's our scaffolding tower in Van from the thermal experiment. And basically we subtract bare soil from the maximum crop height, and we essentially get a pretty good model of the sort of mass of vegetation. And you can see all the rig and furrows showing up beautifully. There's the ditch and quarry field, some sort of enclosure system up here, but sort of outside this stretch. So this works really well. It's quite exciting because using LiDAR to look at crop marks isn't something that's generally being explored. So just to give you sort of another example, basically this is Biddington again. Basically we have our two sites I want to consider. This is our TDR box in the pasture field here. This is where I've been doing my spectrodiometry transects. A1 running off here. And basically this area here is the interface between the clay soils and the sand and gravel terraces. And I just want to compare the returns from both areas. So looking at the sort of west side of the A1 on the clay soil first, here's the ortho photograph from the 27th of June 2011. And you can see we've got kind of little bits of enclosures. We've got a round feature here, which is probably a lovely round house, and these sort of pity things, which I would determine as roof. Looking at the vegetation height model, we don't get anything like as good information from that as we do from the aerial photograph. You can kind of see there's things going on, but mostly because you know they're already there in the vertical photograph. But when we look at the absorption ratio from the Cassie light and spectral, that's actually really washed out on that screen, isn't it? It looks beautiful on here.
It's a bit better on the monitors up here, David. Okay on the monitors up here.
Okay. Basically, we can see a lot more detail in this. Things like this double ditch, kind of segments of ditch up here that, oh no, jumping ahead, wrong direction. Are a little bit more subtly expressed in the aerial photograph. Now, the important thing, I think, from this thing is that no single one of these sensors is giving you best results. But the other thing is, the Cassie hyperspectral data is 1 meter spatial resolution. So the spatial resolution is not be all and end all, but it's considered to be largely by the archaeological community when you compare it to the 8 centimeter resolution. So moving across the road onto the free draining soil, you can see we've got all these beautiful, lovely, complicated, sort of Romano-British settlement crop marks, paleo channels, geological crop marks, post-medieval stuff. And it's lovely. We get really, really good definition on this photograph because, as you can see from the shadows, it's taken in the morning, which is when you really shouldn't do your airborne surveys from the point of view of the hyperspectral, but the geomatics group have done that kindly for us. And the vegetation model basically shows a lot of the same features, not quite as much detail because I think we don't have that sort of shadow relief. But then, interestingly, the absorption ratio shows much less. And bearing in mind these are all data required on the same day. They're about 700 meters apart. It's the same crop, it's the same wheat, all part of the same crop rotation, sown at the same time. Basically, finding the optimal sensor is not just as easy as saying just use this.
So basically this is proving kind of interesting. And I think it's down to the variability of the archaeology, the variability of the context it's in, and the fact we're looking for very small things and very big data, and I haven't even got onto the weather yet. In terms of further work, I'd like to look at the scan angle from the LiDAR, because we have that encoded, so we can actually look at the sort of bidirectional reflectance factor and how that affects the return of that vegetation height model. I need to do more sort of spatial analysis in terms of filtering my inputs and also degrading the bare soil model, because I think it may be possible to use lower resolution data and keep repeating that. And then do a statistical comparison of the different sensors or the features we've identified in geophysics. I'd like to thank NERC RSF, because this is a slide from a different presentation for them, so they're first. It's the Royal Agricultural College in Thornhill Estates for letting me traipse all over their land and molest their crops, and for the view. Thank you.
What we've heard in the last three presentations is the basic data sets that the projects work from. Obviously very disparate and highly complex in their own way. Fortunately, we've got Ant here to explain how they all fit together. So we're done.
Oh, excellent. I'll be able to see what I'm doing. That's not making music. Right. Okay, thank you, Chris. Bringing it all together, thank you, Rob, David, and Dan. This is really about trying to bring together all those different data sets and associated weather data, which I've just said anything about in the introduction. So, broadly, archaeology is a discipline places great reliance on relationships between data, interpretation, practice, and theory. We collect lots of evidence or excavations, as maybe most of us like to call them, and we get more evidence by doing more excavations or more analysis of stuff. And then we start to connect the dots between these things, normally through a process of some kind of theoretical model. And we can produce a whole range of different theoretical models that can join the dots between these different bits of evidence that we collect. And as we gather more and more evidence, we can start to cross off some of these theories that we generate that just don't fit the data anymore. All the theories that we generate have assumptions built into them. We're trying to focus on the ones which use the fewest number of assumptions until we create a quite kind of grounded model which we're pretty confident in as a reflection of the past. Although that model is always a model of the past and it's never really something that's rich enough to represent reality, if reality ever actually exists. Because we have the theories, and so we have different contextual viewpoints in which we can look at the past. And so many of these different models may be equally valid. So great, we have this wonderful build-up of data which we can theorize about, we can produce models about, and we can produce stuff about. Now, if we're starting to extend that, to produce bigger models, to look at national or international frameworks, we actually want to introduce all of those data together. The problem is, how do we start to pull that corpus together? We have the accessible knowledge, the stuff we're aware of, and we can actually get access to. There's the inaccessible knowledge, well, the stuff we're aware of, but it's behind some form of barrier. It might be in a repository which we don't have access to, it might be a paywall, some form of system that means that we just can't get it. Then there's a whole heap of other stuff that goes on that we're not aware of that might actually have some part to play in the solution to a problem we're forming. So we have this potential knowledge cloud. Some of it is accessible, some of it is not. Now in Dart, we have a whole range of different data. And we need to make sure that it has an impact in this landscape. So it doesn't just go in there and just trickle away. We want it to actually change the way that it makes people both think and conduct what they do. And one of the ways we decided to do that was to adopt an open science philosophy. So wherever practical, all the data will be in the public domain as soon as possible in accessible repositories. Remember writing that. It's actually proven quite difficult to do in practice. I can wax lyrical to you, probably over beer at the end of this why it was so difficult. But you know, we've achieved quite a good thing, which I'll now talk about in a bit more detail. The thinking behind this was that by opening up and dynamically sharing this data with a broad consortium, we can improve scientific process, improve results, improve impact, and have a bit more wow. You know, we can build communities of practice, different end users. And our next presentation from David is demonstrating exactly that. So this requires a corpus of open and accessible resources using open methods, open processes, open licenses, open science, bringing in more communities, having science within society. So as part of that, we have our data repository. This is based upon CCAP, the Open Knowledge Foundation. It's called the metadata system. We have explicit licenses, liberal licenses using Creative Commons by attribution and ODDL, so open database licenses, to encourage reuse. The reason why we've got by attribution is so that we can facilitate tracking. We know who's using our data, but we don't know because it's not enforced. We'd like to know. But ultimately, I want everybody to use our data and reuse our data. It has the Open Access Initiative protocol for metadata harvesting. I've mashed that up a little bit, but basically we can share our metadata and it can be harvested by other institutions. So the ADS, the Europeana, can basically get hold of our metadata. The data has a URI, so it can be called in by web processors, which we'll talk about in a little while, and CCAN itself has its own API, so it can be part of a programmable network of stuff. So here is the Dart portal. Within the Dart portal, this is live, by the way, so expect it to break. We have data. We have our hyperspectral, the LiDAR, vertical array photographs, bulk electrical conductivity from dance data, have a look at thermal stuff. So you get a summary of what's going on in each of those data collections, as it were. And within those collections, we have a little bit more information about what's going on there, why the data's been collected. These are all our different data resource objects. We have metadata about the collection itself. The moment we have it, you can cite that collection. Very useful. And a whole range of different metadata tags. Most of it is based upon the ADS metadata system. We've extended that with other metadata frameworks. We have an ingest framework with Deepblue that makes that whole thing very easy to do. And so when the ADS are archiving our data, which we are doing at the moment with geophysics, they should be able to pull everything out dynamically from what we have here. That's the aim. We'll wait and see what it is in practice. Now, we can go down to an object. This one. There we are. So it's me in the thermal, sorry, in near infrared, taken by John. We have a little map where it is. We have specific metadata now about that resource object, and you can reference it individually. So we've got lots and lots of metadata, and we've got lots and lots of resource objects. We have explicit licenses. This stuff can all be reused. Great. So you can access our raw data. You can reprogram models based on what we've done. We've also created an integrated spatial temporal database. This has been modeled in UML, so you can see the entity relationship models between all of our tables and our lookup tables. We've got the definitions and constraints and relationships all in there. We're also able to convert that UML into PostgreSQL specific SQL scripts. So those who use Postgres can basically take all that data and that's gone. This creates one big CSV file, which can be ingested in as a 2 gig file. And this is the environment where it's used for both online data mining. Most of the stuff that I'm writing is done in Python. Again, these are all shared under liberal licenses to encourage reuse. It's based on accessible URIs and potentially accessible databases, and still need to resolve what we're going to do with that database in respect of making it open, i.e. hosting it in an open way. And so basically you can take the code that I generate and run it in your own environment. There is no firewall or no barrier that blocks you from analysing the data in the same way that I do, which I will show you now. So this is my IPython notebook. So in here, this is how we can process our data. The top is telling us the libraries that we want to use. I can just run that script. And now it's going to open up one of our data sets, which is on the server. Okay, and here's a citation for it. So we run it. That's all working. Live demonstration, it actually works. And here's a quick summary list of the data that's just been imported. The next data set here is starting to, sorry, the next process here is starting to group that data. So we've now gridded the raw data into a 20 by 20 array. And we can plot that data. So what you have here is an audit trail, a full process of what we're doing from our raw data to how we kick it out at the back end. So you can see how we've taken our number, or taken that raw data as a numeric array and start to process and transform it. It is completely transparent what we have done in that thing, and we can share that with everybody. So if you want to see how we generated pretty pictures, you can see how we generated pretty pictures. If you want to get an understanding of the assumptions we've made when we processed from raw to interpreted output, you can see what we've done. If you disagree with it, you can do it yourself in a different way. And you can build on these techniques. Right then. So here's the same thing now, but this is based upon the Postgres environment. So we have a few slightly different libraries. We've got a different connection script here. Okay, we still bring in the data. We can still re-array it. But what I've done, okay, so plotting it out here. What I've done now is just create a number of little filters over that data. And plot those out and create something that brings them all together. Wonderful, easy life. But we can also very rapidly reapply that to other elements of our data. So I know here that I want to look at sensor configuration, C, for example. And we can rerun the whole process. You see we now don't see the ditch feature come through in our raw data. You can possibly see something here, probably better on the monitors up there. But if we run through on our different filters, you can see that we're getting something very clear when we're using with the data. But again, this is a process we can share, it's transparent, it's open. It's very easy for people who are reinterpreting or reanalyzing this data to see what we've done and to look at the whole process that we've used. Okay, so the whole point of that is to start to improve engagement, data, collaborations, science, impact, and potentially serendipity. Yeah, how we can just get people to look at data and just do interesting things because they can. So we're opening up our data. One is a reduction in data mountain. There's value-added resources that actually can be reused. There's huge engagement potential and huge social good. It's access to traditionally inaccessible data. Hyperspectral data is quite difficult to get hold of, or it needs to rarely get hold of the archaeological community. If we're also opening up our processes, we should be able to get more eyeballs looking at our code, making sure that the processes are actually robust as well as transparent. So we should be able to generate better models. And we can start to deal with some of these trust, provenance, and credibility issues, which are problems within the open data community. It's not just kind of science element, but it's also what's going on with governance and their open data issues. We then have open practice, say more people looking at the data. looking at the processing itself and trying to improve that. So increased understanding, increased transparency and reuse. We're not generating black boxes. We're not just clicking the button and getting something coming out the other end. We're understanding that transformation process. Collaborations. We can start to converse and engage more effectively with that whole cluster of different organisations that are affiliated with what we do. So Mock from Royal Agricultural University speaking this afternoon. We are now, discussing this afternoon. But we can start to look at how there is synergy between the goals that we want to do as heritage professionals and what the farmers at Royal Agricultural University and researchers at the RAU are doing as part of their day-to-day activities. Some areas there is significant overlap, and we are always a core partner. We need to work with these communities if we're going to have a much larger impact and to deal with stewardship, not just on a local level. We're talking about ramping this up at both an international scale as well. Improving impact. More reliable models should lead to better decision-making processes, better understanding. We should have easier reuse and engagement facilities because we're providing this in well-understood and open formats. And this whole serendipity thing, which I do really buy into, we've got this free flow of ideas, this free flow of data that allows people to model in very effective ways and model without having to spend their time writing grant applications to get to small bits of data. It's there and it's reusable. And it's open citizen science, producing something where you can have variations in different communities of practice, different community groups that come together to solve problems which they address. It doesn't have to be a major research problem, it doesn't have to be major impact. It's something that a small or large scale community will just resolve on their own. So, why do this? The EU says so. Open infrastructures for open science. Good science diversity matters. Enabling this is not just good for science, it's also necessary for smart decision making. So, it's ticking the boxes for the EU. UK government says so. Data to optimise its value to society must be open, shareable, and where practical, it should be free. This is a document that came out only a few months ago. Royal Society says so. Science is an open enterprise. Recent decades have seen an increased demand from citizens, civic groups, and non-governmental organisations to bring scrutiny the evidence that underpins scientific conclusions. So we're looking at evidence-based research. We're looking about the impact of evidence-based science in policy, in curation, in the whole range of different activities which we undertake on a daily basis. EPSRC says so. EPRC-funded research data is a public good, produced in public interest, should therefore be made freely and openly available. So, that's our data. It's openly accessible. Please use it. Thank you.
So Sam has described the availability of the data sets that the project have produced, and I'm going to talk a little bit about how one may actually use these sorts of data sets as an outsider.
Yeah, absolutely. I'm an outcome.
Got an impact, David.
Sorry? Impact. I have an impact. That's right. Okay, so I'm David Jordan. I work at the Geoscience Institute at the University of Mainz in Germany, and I'm a soil geoarchaeologist. So I spent most of my life using soil methods to look at the structures of the stratigraphy of archaeological sites. Let me bring this to an end. Get mine. I just added a slide to my show, if it recognises it. No, it doesn't. Oh, well, never mind. I'll use the original one to talk about what I was going to show. Okay, so in Mainz we are working on the detailed analysis of the structure of archaeological deposits to try and understand their detectable behaviours. In other words, we're using geoarchaeological approaches, micromorphology, the analysis of the electrical conductivity, the electric properties and so on, within the soil at a small scale, using samples taken from excavations and from field survey data to understand the properties that we then go on to detect. And central to this is being able to describe some of these properties in a more rigorous way, where we can numerically, using models. And that's what I want to talk about today. What I've been involved in the DART project is really very much an extension of the work that you've seen being done by the students and what's being presented for them. And I have to say first that I'm very grateful to DART for giving me this opportunity. So here we have a typical archaeological representation of a set of typical archaeological features, prehistoric ditch, and the drawings we make of them. These are our starting models in many circumstances, representing this extremely complicated physical reality in a relatively simple way. We know from many years of field experimentation and in archaeology and before that in geology and in engineering that we can create, and here is a very simple modelling tool, a representation of distributions of, for example, electrical resistivity in the ground, looking vertically down through the ground, and generate from that our expectation of the detected distribution of resistivities at the ground surface, and then compare them with what we actually see when we do a survey. And this kind of modelling process is extremely common in engineering and geology, as many of you will know. The models that we generate, the models that we can use can also be based on our understanding of the fundamental physics of the soil. So here we have two equations, the Rhodes equation and the Waxman-Schmitz equation, developed both of them very many years ago. The Waxman-Schmitz equation based on the RQ equation, which was first published in the 1940s, based on much earlier work, describing electrical conductivity, electrical resistivity, or 1/over resistivity in each case, within soil and shaly rocks in terms of more fundamental properties. The Rhodes equation describes conductivity in terms of two pathways through the soil, a wet soil pathway and a direct pathway through the soil conducting through macro pores. And here we have something similar for the shaly rock conductivity, where we have a formation factor, which is a geometric factor, and the resistivity of the water within the rock, and a term describing conductivity through the clay within the shales. Essentially, the important point is that we can predict from certain known properties the kind of electrical conductivities that we would expect in specific circumstances. Having done that, we can build crude models of archaeological structures. Here's a very crude ditch, consisting of a series of layers, a cultivated horizon at the surface and stratigraphy beneath, and from that predict what we would expect to see using electrical resistance tomography of the kind that we saw earlier from rock at the ground surface. And by using models of this kind, we have the liberty to change conditions without having to go into a field and pour water on it. We can create mathematical representations of reality which we can then adjust. Now, this raises all kinds of difficulties. Realistic models of the behaviour of soils are extremely difficult to make. They're very difficult to do because soils are extremely complex, diverse, and exist within diverse environments, rainfall and so on. Archaeological remains are vastly more complex because they are not only complex in themselves and very diverse, they interact in complex ways with their environment. And soil, hydrology, structural archaeological remains are very variable at many scales, so why bother? Firstly, we have real problems, as the DART project itself has been based on this question of targeting our methods, the right methods in the right places at the right time of the year. So our motivation for understanding the mechanisms, as been explained to us already, is very strong. Secondly, we do modelling anyway. When we decide, for example, as commercial operators going out and doing surveys, what methods to apply where and at what time of year, we are making assumptions which we cannot usually challenge because they're not terribly explicit. We say more or less it's like this at this time of year at that time of year, and that's wonderful, but our models are very difficult to challenge while they remain relatively relatively fluid in the way that they're stated. So getting better, I'll come back to that point. So, what I was doing several years ago was creating models of typical ditch structures like this, adjusting the water contents at different times of year, and using equations like the Rhodes and Waxman-Schmidt equations to calculate the contrast that we would see in resistivity using typical electrical resistance arrays. And here is the difference between a contrast in summer and a contrast in winter, similar to the kind of pictures that you've been seeing already from what the students were doing. Here is the excavation of the ditch at Diddington, and I wanted to show you this because you can see we're down to a level of saturation at the top of the gravel at the bottom there. And from this, we generated a description of the hydrology of this material. Why the hydrology? Why is this important? Well, again, we've already heard that the water content in the soil controls a great deal of the geophysical properties that we then go on to detect from the ground surface. And here I'm using a modelling system called Hydrus, very widely used. And here is approximation to our Diddington ditch, not in the clay field but in the gravel field, with the various elements to it, taken directly from the recording. And on the right-hand side in the field, and on the right-hand side you can see two different stages within the model using the rainfall data that I got from Cambridge Botanic Gardens, the nearest place that I could get reliable rainfall data daily, because we didn't have it from the site itself, showing changes in water content derived from the hydrological model 14 days, 2 weeks before the final period of fieldwork, and on the day of the final period of fieldwork itself. These compare reasonably well, the second one with the measurements of water content we've derived from our own measurements in the laboratory. So we know that the model is not far off the truth. What we then did was output this distribution of water content and other properties and use it using one of these equations to calculate the expected distribution of values of electrical resistivity within the different strata. And the idea is that we compare this with reality to see how well the two compare with each other. So this is an inversion of one of the data sets from Rob's work. Thank you very much indeed, Rob, for this information. And here is our distribution of the resistivity values that we have calculated from the hydrological model and the geophysical model together. There are all kinds of things wrong with it. We don't model the boundaries between the different volumes of material at all well. Our understanding of the behaviour of the gravel underneath, which is saturated but resistive, is poor. The reason for this is the models are not entirely appropriate. The Rhodes equation, which we have used to create this distribution, models the behaviour of gravels very badly indeed. And so we need a different approach to it. And that's something that we're looking at investigating at the moment, in a moment of time. But nonetheless, these provide us with tools to extend the data gathering that the students of that project have been undertaking and explore the way we, the sort of physical properties come about in a more flexible way. And what we are doing at the moment is carrying out laboratory analyses of the electrical conductivity against water, water against dielectric permittivity, and other properties to try and improve these models and tie them down to the distribution of physical reality in the ground. That's work very much in progress, and so I can't report on the details of that yet, but that is really something where we look forward to working with the students in developing this further. Now, one of the big problems that we're having is the way that we translate the reality of structures in the ground into the archaeological record. Because we do this by dividing up areas of our soil into strata. However, our boundaries really aren't like this. The reality of the distribution of materials in the ground is very, very continuous. And if we